Hi there, we are live. My name is the Duke Dev, and what I'm gonna do now is I think I'll take maybe 2 hours out of my uh, after work time and learn something. I usually stream at night, and I realized that that probably isn't the best idea because I get tired and it's late and I have no focus and I'm already drained. But you know, right now I finished my work. I'm gonna do a streaming session of, I hope, 2 hours. I think 2 hours daily of learning a new skill is beneficial. It's enough. It's not much. It's not little. Okay, so let me start. But before I even do something, let me just check if I'm speaking. I hope I am. Am I speaking? I am. All right. So, hello and welcome. I forgot to change my wallpaper. I'm leaving this one. I like the colors, but look at this now. Look at this now. This is my tablet. First things first, I removed the top bar on the Windows. I first tried using Unite, which is a package for Ubuntu, which works fine, but it removes it for all the Windows. I only wanted for the specific ones that I needed, especially for this one, which is actually my tab, on which I'm sharing my tablet. So I removed it. I just installed something called, let me just write it here, something called Devil Spy 2, which is, if I'm not mistaken, let me just put this. Devil Spies 2, what's Devil Spy? Devil Spy is a window matching utility allowing the user to perform scripted actions on Windows as they are created. For example, you can script a terminal program to. Okay, yeah. So basically, it manages and manipulates Windows on Linux. Is it Linux specific? It's based on a specific flavor of it. Doesn't say. Okay. So yeah, that's basically it. The second thing that I wanted to show you. So the first thing I wanted to show is the wallpaper. I like it. I really like it. It's a nice one. And the second thing, so let me just, so this is my wallpaper. And now this is my tablet wallpaper. So let's do this. Just a second then. Okay, doesn't matter. Oh, so let's do this. What I did in the last episode was that I have a book on deep learning called Python Deep Learning, exploring. What's the name of this book? It's Python Deep Learning, exploring deep learning techniques and neural network architectures with PyTorch, Keras, and TensorFlow. So yeah, I won't overly advertise it. So just so you know, I'm following a book here, and I think I came to the point in which I'm talking about linear and logistic regression. I don't want you on the side, I want you on the top. I want you on the top, yes. Linear and logistic regression. So what are we talking about here? Regression algorithms are a type of supervised algorithm that uses features of the input data to predict a value, such as the cost of a house given a certain feature. I think I already walked through this in the last episode. Oh, I have it here, so I don't need to write a new chapter. So I'm just gonna walk over this from here. So there are certain features of the house, such as the size of the house, such as the age of the house, such as the number of the bedrooms, such as the number of floors, location, stuff like that. So what regression analysts try to do is they try to find the value of the parameters for the function that best fits an input dataset. So what do we have? We have something called a cost function. This is the thing that I circled right now. So the cost function is the function of the error, and we try to minimize it by finding properties or weights or parameters for the function over the input data that best approximate the target values. Yeah, the cost function is the function of the error, and the popular one is called MSI, which is the mean square error. Okay, we take the square of the difference between the expected value and the predicted result. The sum over all the input examples gives us the error of the algorithm representing the cost. Okay. So I think here I also have an example of this. Let me just increase this to 20. So it's, yeah. So let's say I have only two parameters. I have the size and the bedroom numbers, and I have the x, which is the vector of size and the bedroom numbers. And I can have here an x of 1,503 bedrooms, and I have the weights of the size and the bedroom. And now I need to, for example, if a house that has these parameter costs 100,000 euros, I'm wondering what the house that has these many meters, square meters, and these many bedroom numbers will cost. And this is the MSI, or the mean square error. So we need to find a vector of weights. So in this case, we have only two of them. Oops, two of them, but we need to find a vector of weights so that the properties we have, such in this case, 500 times V1, this is the size, plus 3 times V2, which is the bedrooms, is equal to 100,000. So we can import other parameters that are gonna fit inside this function. Okay. And if we had more houses, we could repeat the same process for every house. And we are searching for a single vector that can predict the correct value that's close enough for every house. Okay, so how can we train a linear regression model? We will initiate the vector v, or the vector with weight. Just I'll just open ChatGPT. Yeah, so I can have it in case. So I can have it in case I need it. Where are you? Here. Okay. Regression. So what we can do here, we can initialize the vector with some random values. Then we create a loop. Initially, the cost function will be 0. And then for every sample that we have, okay, mean square error. And then we use gradient descent to update the weights with v based on the MSIs until MSI falls below threshold. Okay, we iterate over the training data to compute the cost function. Once we know the value of MSI, we'll use the gradient descent algorithm to update v, which are the weight vector. To do this, we'll calculate the derivatives of the cost function with respect to each weight, vi. So we'll know how the cost function changes with respect to individual v's, weights. Okay, interesting. Another example of regression is called logical regression, and we are using logical regression in order to get categorical data. For example, whether the house is overvalued or undervalued. 1 for overvalued and 0 for undervalued. And for this we use, as I said, logistic regression. In linear regression, the output is the vector x times the vector weights. So this is the logical. Well, sorry, this is the linear regression. So what do I have? I have x times weights. But here the output will be a special logistic function. Okay. Logistic regression. So it's gonna be rho x times the weights. So what is happening is that the value of the vectors will be squashed in a certain interval, in this case 0 to 1. Okay, the logistic function is a probability, and the closer the results to 1, the more chance there is that the house is overvalued, and vice versa. Okay. Now let's talk about something else. Let's talk about. So this is, I think, just an introduction. I'm looking at the book. This seems like an introductory kind of chapter, meaning that I won't go deeply because I assume that we will do this hands-on in the future chapters. So the second thing that I wanted to mention is something called SVN, or support vector machines. So this is a supervised machine learning algorithm. It's used for classification. And S7 tries to apply the hyperplane. Hyperplane. What the hell is a hyperplane? We separate the samples in that set. So a hyperplane is a plane in a high dimensional space. A hyperplane in a one-dimensional space is a point, and in two-dimensional, okay, without looking at the book. So what can a hyperplane be in a two-dimensional? It's a line, right? It would be just a line. So in three-dimensional spaces, in 3 dimensions, you would have something like a sheet of paper, and that would be a hyperplane. Now, going further on, talking more dimensions, I don't want even to imagine this, but yeah. So once we have defined our features, every sample dataset can be taught as a point in a multidimensional space of features. One-dimensional that space are the possible values of one feature, and we have the coordinates of a sample are the specific values of each feature for that sample, and then we will draw a hyperplane to separate points with different classes. Okay. Enough about SVNs. Let's talk. We also have decision trees. Now, decision trees are another popular supervised algorithm. So what a decision tree does, it creates a classifier in the form of a tree. And we have nodes, and we test the specific attributes and how they are performed. Okay. So what this does is we create a tree, and let's say this is a car sorry, these are the car dataset. And let's say we have, I don't know, mileage that's more than a certain number, and we know that this is, for example, an Audi. Otherwise, we can have stuff like comfort greater than this. We can say, oh, this is a Volkswagen, or is it the other way around? Or it can be a BMW, stuff like that. So these are decision trees. Again, I won't go too deep into this because I hope we will do more of this in the chapters. In the coming chapters. And now, let's start. I'll skip all of these other algorithms, other basic machine learning concept techniques. Let's do. Sorry, let's do. Let's do neural networks. So I hope now I hope to understand what the neural network is, what it does, how it works, and all the other stuff. For anyone who's joining the stream right now, my name is the Duke Dev, and this is my first time actually grasping concepts such as these. So it's my first time learning this, so to say. Okay, so what are neural networks? What I know about them is, I hope I can draw this properly. Sorry, this was supposed to be a brain, but it looked like a butthole. So neural networks were inspired by the brain that we humans have. But the brain, emulating the brain of looked like a quite complex endeavor. So what we did is, instead of trying to model the brain, we used neural networks in other specific tasks, like computer vision, NLP, speech recognition. Okay. There's something to open here. There's a link in the, which I just need to type. Large scale visual recognition challenge. So what this is, image large scale visual recognition challenge. What is this? The ImageNet large scale visual recognition challenge evaluates algorithms for object detection and image classification at large scale. One high level motivation is to allow research. Okay, so this is like a bootcamp of some kind. Okay, I haven't, again, a lot of these concepts are Greek to me, so I'm still quite confused, but I think as I'm going through it, I think this will become clearer. Oops, hopefully. The participants train their algorithm using the image database. Ah, okay, so they have a database of their own. So cars, people, trees, and so on. Okay, so now let's dive deep into neural networks. So a neural network is a mathematical model. Let me see how ChatGPT would define it. How would you, in simple terms, define what neural networks are? Neural networks are a type of computer program designed to mimic how the human brain learns. They consist of layers of connected neurons, which are processing units that work together to recognize patterns in data. Just like our brains learn from experience, neural networks learn by adjusting connections between neurons based on the data they see. Many pictures of cats and dogs, they learn to identify features that are more likely to belong to a cat than a dog. Okay. Okay. So, what are the characteristics of a neural network? We have something called neurons, that is the place where information processing occurs. And neurons are connected using connection links. Connection links between neurons can either be strong or weak, and based on this we process data differently. So each neuron has neurons, each of them has an active state of its own. And each neuron has an activation function. So what a neuron is actually is a mathematical function that takes one or more input values and outputs a single numerical value. In terms of neural networks. What are neurons? I realize that ChatGPT has a knack for describing things simply, even if it uh, talks about complex things. It explains stuff in a much more streamlined way uh, than the books, the textbooks. In neural networks, a neuron is a small unit of computation similar in concept of biological neuron in the brain. Each neuron receives one or more input values, processes them, and produces an output. So we have inputs. A neuron receives values from other neurons directly from input data. Then we have weights. Each input is multiplied by a weight, which determines how much influence that input has on the neuron's output. We have summation. So all these weights are calculated in the neuron. Activation. Okay, so this is the activation function. This function introduces non-linearity, allowing the neural network to solve complex problems by deciding whether to fire or stay quiet. I think someone wrote on Reddit or somewhere that most of the machine learning algorithms are just glorified conditional if-else models, which I have no idea if that's true, but by looking at it, this seems like this, but on a much higher scale. The neuron activation function, this function. Okay. So how does this work? I have some input here. Add another one here. Add another one here. All the way down to here. These are the inputs. Now we have the weights. Here, I don't know what B means. This is V1. This is V2. And this is Vn. Now this is a neuron. So what do we have inside it? We have the activation and the activation function. So all of these guys are coming here. I was drawing the whole time, and so all of these guys are coming here. Then this activation streamlines the output of this to the activation function, and then get a real output. So these are the different elements of a neuron. And the neuron is defined as follows. Okay, so I have epsilon. Okay, it's a different shade of. So we have function. We have the sum plus b. Okay, so this is, it says here, this is how the neuron is defined, but this doesn't tell me anything. So let me just do this. In the book it says that the neuron is defined by a certain mathematical formula in which we sum the values of xi of values of the multiplication between xi and weights I. Can you explain this, please? The formula referring to is the foundation of how neurons work in a neural network. Yeah, that's the one. In mathematical terms, a neuron outputs can be represented by the following formula. So what are the inputs? So these are the values, the x's are the values coming into the neuron. Okay, so what is x? X is a different feature of the data. Like the size of the house, like the number of rooms. Okay, yeah. Weights, yeah. So these are the weights for each of the inputs. The neuron learns them and adjusts them over time. Why do we have the summation? For each input, we multiply. Yeah, but why? Why? What's the... You know what? One thing that I didn't like when I started learning programming is the fact that you know, some things are just not meant to be known. I remember asking how the while loop works, and they're all like, it loops for as long as you created it triggers the same piece of code, the same chunk of code over and over again. But I was asking, yeah, but how it works, you know, on a lower level? What's the logic behind it? How it triggers? How it knows to? I mean, I'm working on a project in which I'm building my own Lisp, and now it makes a lot more sense to me now. But back then I was really mad for not understanding it and for not having it explained. But at what point I think people just say, you are not supposed to know this. You are using your tools for your own good. You know, it's the same thing as, you know, you have a car and you drive a car, and I'm not that interested in how a car works under the hood. And I know that there are a lot of different components that make a car run, from the ignition mechanism and the battery and the motor and everything else. And I know that some people want to know with this and want to learn this, and some people are not complete without having this information at them. So what I'm gonna do now is ignore all the things that I don't know. For example, why we sum stuff. Bias. And output. The output, the result of this summation plus the bias is then passed to an activation function which introduces non-linearity. Example, if you have 3 inputs, then the neuron's output without activation would look like this. The combination of inputs and weights less. Okay, so what happens once we get a net value. Okay, once we calculate epsilon, we pass it to the activation function. And go to the next. Okay. I'm feeling the puzzle. I'm feeling the puzzle in my mind. Okay, the book says the same thing. We compute the weighted sum of the inputs, which is this, of the inputs and the weights, which is the and this is called the activation value. So x is a numerical value or an output of other neurons. And the weights are numerical values that represent either the strength of the inputs or the strength of the connections between the neurons. Mm-hmm. Mm-hmm. So what do we do then? We use the result of the sum as an input to the activation function f. And the activation function f is also called a transfer function. They all have to be non. What means if something is non-linear? What means this? What means this? Let's go back to ChatGPT. What is a dot product between two vectors? It seems like my mic isn't catching my mechanical keyboard. I need to fix. Let me just get my Red Bull. I'll be back there. I'll be back in a second. Okay, I'm back. So what was I talking about? Yeah, the dot product. The dot product or scalar product. It's a mathematical operation that takes two equal of numbers and returns a single number. This result represents the extent to which the two vector points in the same direction. So I have two vectors, A and B. And this is the dot product. Yeah, I know. I already knew this, by the way. So if this is the dot product, so what else? If we have two vectors, this is the dot product, and what? Okay. What idea is the dot product giving me? The dot product can also give us information about the angle between the vectors. The dot product is positive. The vectors point in the roughly same direction. 0, the vectors are perpendicular. Or negative, the vectors point in the opposite directions. So wait, so if the dot product is 0, they are perpendicular. The angle is p divided by 2. If it's greater than 0, they point to the same direction. Otherwise, but they're not pointing to the same direction. They're what does it say here? Roughly the same direction. Okay. Let's do this back. Bring this back. So do we have an example for this? So the activation function is f of x equals x. And we only have one input value. So what will the output of this be? Vx plus b. This is the linear equation. This gives me a line, right? So in one-dimensional input space, the neuron defines a line. I didn't get it properly. Okay, let's talk about the layers now. How long am I streaming? 50 minutes, I think. Let me think about it. I think an hour and 50 minutes is good for this. And then I'm gonna switch back to C. I need to cleanse my palate. After this, this really, I don't know if it's complex, but it's confusing for me. It's something that is new. It's strange. It's wild. So. Okay, so neurons are organized in layers. Layers are connected between each other. So the input layer is the data set and the initial conditions. If we have a grayscale image, the output of each neuron is in the input layer is the intensity of 1 pixel of the image. Okay. So I get this. For this very reason, we don't generally count the input layer as part of the other layers. Okay. Okay, so there are cases in which the output layer can have more than one neuron. And you will have 10 output neurons. Each neuron corresponds to a digit from 0 to 9. Okay. So the output layer has 10 neurons, and each of them represents a digit, in a sense. Okay. Um. All right. What? Wait. I need this. I'm gonna close this. What is a one layer feed forward network? A one layer feed forward network is the simplest type of neural network. It has only one layer of neurons between the input and the output. And this is the output layer. This network type doesn't have any hidden layers, which means all input nodes are directly connected to the output layer without any intermediate processing here. So we have an input layer. Draw this. So what do we have? Is an input layer. So let's say this is the input layer, and we have here x1, x2, x3, all the way to however many we will have. And let's say we have some outputs such as v1, y2, yn, and all between we have stuff like b1, so these are the weights, v1, v2, v3, v4, v5. Does and then I have, I don't know, v2, and then I have v2, wait, this is v11, v12, v12, v13. Okay, I don't even want to try this, but basically I think I get what this means. Is just one layer, we have an input, then just one layer of neurons, and then we have the output. That's it. I hope we start with something concrete here, because I got so much theoretical information here, and I need to use this. I need to use this to know how this works. I can't just read stuff. So okay, so we have single layer networks. We also have multi-layer networks. And extra layers are called hidden layers. The following diagram that demonstrates a 3-layer fully connected neural network with 2 hidden layers. Okay. All right. So we have, I don't know why I removed this. We have layers. We also have the activation function. So there's something in the book that really confuses me. This is this. Can you please break the paragraph? Can you please break and explain the paragraph about what does it mean to classify linearly inseparable classes? What is the difference between a linear and non-linear function? Before I even continue reading this chapter, I need to make sure I understand this at least. Classifying linearly inseparable classes. Linearly separable classes. These are classes or groups of data points that can be separated by a straight line or a plane or a hyperplane in higher dimensions. Visualize a hyperplane in higher dimension. How does it look? Higher dimension.
In this video, we will look at a geometrical problem in many dimensions. But don't be scared, there will be no formulas and we will start in 2 dimensions. Let's create a square with side length 1. Inside the square, we place 4 blue circles, 1 towards each corner. They have diameter 1/2, so they fit exactly inside the square.
Sorry, I thought I thought my tablet was on.
2 dimensions. Let's create a square with side length 1. Inside the square, we place 4 blue circles, 1 towards each corner. They have diameter 1/2, so they fit exactly inside the square. This leaves an empty region in the center where we place an inner circle. We are interested in the size of the inner circle. We will consider generalizations of this figure in 3, 4, and more dimensions, and we will be interested in the size of the inner circle, or hyposphere as it is called, in higher number of dimensions. The question we ask is, what happens to the size of the inner hyposphere as the number of dimensions grow? The surprising answer is that the inner hyposphere grows without bound. Already in 10 dimensions, it is so big that it stretches outside of the hypercube that contains the blue hypospheres. In the 2-dimensional case, an inner circle of that size would have to overlap with the blue circles, but we don't allow any overlap. So how can this happen in 10 dimensions? How can the inner hyposphere grows without bound? Interested in the size of the inner circle, or hyposphere as it is called, in higher number of dimensions. The question we ask is, what happens to the size of the inner hyposphere as the number of dimensions grow? The surprising answer is that the inner hyposphere grows without bound. Already in 10 dimensions, it is so big that it stretches outside of the hypercube that contains the blue hypospheres. In the 2-dimensional case, an inner circle of that size would have to overlap with the blue circles, but we don't allow any overlap. So how can this happen in 10 dimensions? How can the inner hyposphere extend outside the hypercube when it is also between the blue hypospheres, which are all inside of the hypercube? A mathematician may explain it using pure equations. An alien might be able to visualize it directly in 10 dimensions. An artist may draw a crazy interpretation like this, illustrating the strange fact that the red hyposphere extends outside the boundaries. But crazy as it is, this figure is not based on the underlying math, and it doesn't explain anything. Let's look at the situation in 3 dimensions. We create a cube with side length 1. Inside the cube, we put 8 blue spheres, with diameter 1/2, 1 towards each corner. In the empty space in the center, we put an inner sphere that touches the blue spheres. How big is the inner sphere in this 3D case compared to the 2D case? Can we understand this visually? To do this, we make a 2-dimensional cut through the cube, like this. The cut follows 2 opposite edges of the cube and goes through its center. The cut only passes through 4 of the blue spheres, and they appear as circles. The inner sphere also appears as a circle in the cut. Note that the cut of the 3D figure is somewhat similar to the 2D case, but there is an important difference. The cut creates a rectangle, which is stretched out such that there is more space between the blue circles in one direction.
Yeah, this makes sense.
This extra space...
Wait, let me think about this. So, in 2D space. In 2D space, it's only a plane. So we only have 2 dimensions. And this circle in the middle is bounded by the 4 circles around it. in 3 dimensions. So why did we cut it from the diagonal? Why didn't we cut it like a cake?
Allows the inner sphere to be bigger in the 3D case compared to the 2D case. What happens in 4 dimensions? It is difficult to visualize 4 dimensions, but we can make a 2-dimensional cut in much the same way as we did in 3D, and look at that. Just as in the 3D case, the cut follows 2 opposite edges of the 4D hypercube and goes through its center. In this cut, 4 of the blue hyperspheres are visible, as well as the inner hypersphere, so the cut looks much like the cut from 3D, but it is stretched a bit more. This is because it contains the diagonal of the hypercube, which is longer than the diagonal in the 3D cube. Because of this additional stretching, there is even more space in the middle, allowing the inner hypersphere to be even bigger. The same technique works in any number of dimensions. Let's look at the 2D cut of the 10-dimensional figure. The hypercube appears as a stretched rectangle in the cut. It is stretched quite a lot since it contains the hyperdiagonal of the 10-dimensional cube. 4 of the blue hyperspheres show up as a circle in the cut. Note how far apart they are spaced in the diagonal direction of the hypercube. Finally, we can see the size of the inner hypersphere, how it extends outside of the boundaries of the hypercube. We can see why this happens. It is because there is a lot of room between the blue hyperspheres in the diagonal direction. What can we learn from this? A direct learning is that diagonals along
I don't like this.
In this video, we will look at a
How to visualize higher dimensions. I need to do this. I'm sorry. I didn't like this. So let me just write here before I even continue. So let's continue our deep learning from the activation function chapter. I'm gonna give this an OK. Remove, remove All right.
Math is sometimes a real tease. It seduces us with the beauty of reasoning geometrically in 2 and 3 dimensions, where there's this really nice back and forth between pairs or triplets of numbers and spatial stuff that our visual cortex is good at processing. For example, if you think about a circle with radius 1, centered at the origin, you are in effect conceptualizing every possible pair of numbers, x and y, that satisfy a certain numerical property, that x squared plus y squared is 1. And the usefulness here is that a lot of facts that look opaque in a purely analytic context become quite clear geometrically, and vice versa. Honestly, this channel has been the direct beneficiary of this back and forth, since it offers such a rich library of that special category of cleverness that involves connecting 2 seemingly disparate ideas. And I don't just mean the general back and forth between pairs or triplets of numbers and spatial reasoning. I mean this specific one between sums of squares and circles and spheres. It's at the heart of the video I made showing how pi is connected to number theory and primes, and the one showing how to visualize all possible Pythagorean triples. It also underlies the video on the Borsuk-Ulam theorem being used to solve what was basically a counting puzzle by using topological facts about spheres. There is no doubt that the ability to frame analytic facts geometrically is very useful for math. But it's all a tease, because when you start asking questions about quadruplets or quintuplets or 100 tuples of numbers, it's frustrating. The constraints on our physical space seem to have constrained our intuitions about geometry, and we lose this back and forth. I mean, it is completely reasonable to imagine that there are problems out there that would have clever and illuminating solutions if only we knew how to conceptualize, say, lists of 10 numbers as individual points in some space. For mathematicians, or computer scientists or physicists, problems that are framed in terms of lists of numbers, lists of more than 3 numbers, are a regular part of the job. And the standard approach to actually doing math in higher dimensions is to use 2 and 3 dimensions for analogy, but to fundamentally reason about things just analytically, somewhat analogous to a pilot relying primarily on instruments and not sight while flying through the clouds. Now what I want to offer here is a hybrid between the purely geometric and the purely analytic views, a method for making the analytic reasoning a little more visual in a way that generalizes to arbitrarily high dimensions. And to drive home the value of a tactic like this, I want to share with you a very famous example where analogies with 2 and 3 dimensions cannot help because of something extremely counterintuitive that only happens in higher dimensions. The hope, though, is that what I show you here helps to make that phenomenon more intuitive. The focus throughout will be on higher dimensional spheres. For example, when we talk about a 4-dimensional sphere, say with radius 1, centered at the origin, what that actually is the set of all quadruplets of numbers, x, y, z, w, where the sum of the squares of these numbers is 1. What I have pictured here now is multiple 3-dimensional slices of a 4D sphere projected back into 3 dimensions. But it's confusing, and even if you do wrap your head around it, it just pushes the question back to how you would think about a 5, or a 6, or a 7-dimensional sphere.
Oh god.
And more importantly, squinting your eyes to understand a projection like this is not very reflective of what doing math with a 4D sphere actually entails. Instead, the basic idea here will be to get very literal about it, and to think about 4 separate numbers. I like to picture 4 vertical number lines with sliders to represent each number. Each
Just a second.
configuration of these sliders is a point in 4D space, a quadruplet of numbers. And what it means to be on a 4D unit sphere, centered at the origin, is that the sum of the squares of these 4 values is 1. Our goal is to understand which movements of these sliders
Sum of the
correspond to on a 4D unit sphere, centered at the origin, is that the sum of the squares of these 4 values is 1.
sum of the squares of these 4 values is 1. So just a second. So if I'm doing this, I have an x and an epsilon coordinate. Is it 0, 0? No, it's not, because yeah, this doesn't work because 1 plus 1 is 2. Wait.
How to draw 4, 5, 6.
Okay, I'm gonna also take a look at this, but wait. What are the possible solutions of x squared plus epsilon squared equals 1? The equation x squared plus represents a circle centered at origin 0, 0 with a radius of 1. The solution of this equation are the pairs that lie on the circle. In other words, any x epsilon point that satisfies this is a solution. Okay, interesting.
Our goal is to understand which movements of these sliders correspond to movements on the sphere. To do that, it helps if we knock things down to 2 dimensions where we can actually see the circle. So ask yourself, what's a nice way to think about this relation, that x squared plus y squared is 1? Well, I like to think of the value of x squared as the real estate belonging to x, and likewise the value of y squared is the real estate belonging to y, and that they have a total of 1 unit of real estate to share between them. So moving around on the circle corresponds to a constant exchange of real estate between the 2 variables. Part of the reason I choose this term is that it lets us make a very useful analogy, that real estate is cheap near 0 and more expensive away from 0. To see this, consider starting off in a position where x equals 1 and y is 0, meaning x has all of the real estate to itself, which in our usual geometric picture means we're on the rightmost point of the circle. If you move x down just a bit to 0.9, the value of x squared changes to 0.81, so it has in effect given up 0.19 units of real estate. But for y squared to increase by that same amount, y has to move an entire 0.44 units away from 0, more than 4 times the amount that x moved. In other words, x changed a little to give up expensive real estate, so that y could move a lot and gain the same value of cheap real estate. In terms of the usual circle drawing, this corresponds to the steep slope near the right side. A small nudge in x allows for a very big change to y. Moving forward, let's add some tick marks to these lines to indicate what 0.05 units of real estate looks like at each point. That is, how much would x have to change so that the value of x squared changes by 0.05? As you walk around the circle, the trade-off in value between x squared and y squared gives this piston-looking dance motion, where the sliders are moving more slowly away from 0, because real estate is more expensive in those regions. There are just more tick marks to cover per unit distance. Also, a nice side effect of the term real estate is that it aligns naturally with the fact that it comes in units of distance squared. So the square root of the total real estate among all coordinates gives us the distance from the origin. For a unit sphere in 3 dimensions, the set of all triplets xyz where the sum of their squares is 1, all we have to do is add a third slider for z. But these 3 sliders still only have the 1 unit of real estate to share between them. To get a feel for this, imagine holding x in place at 0.5, where it occupies 0.25 units of real estate. What this means is that y and z can move around in the same piston dance motion we saw before as they trade off the remaining 0.75 units of real estate. In terms of our typical way of visualizing a sphere, this corresponds to slicing the sphere along the plane where x is 0.5 and looking at the circle formed by all of the choices for y and z on that sphere.
So what is this? This is the sphere in 3-dimensional space, and we created a slice on x, a piece of the cake, and at x we have our sphere locked to 0.25. So then we are just moving around its border at this point of 0.25, and the rest of those values are shared between epsilon and z.
As you increase the value of x, the amount of real estate left over for y and z is smaller, and this more constrained piston dance is what it feels.
Okay, so that's the x. I'm trying to visualize it. It's not very intuitive, so I'm trying to visualize it. X is this. That's x. That's x.
Feels like for the circular slice to be smaller. Eventually, once x reaches the value 1, there's no real estate left over, so you reach this singularity point where y and z are both forced to be 0. The feeling here is a bit like being a bug on the surface of the sphere. You are unable to see the whole sphere all at once. Instead, you're just sitting on a single point, and you have some sense for what local movements are allowed. In 4 dimensions and higher, we lose the crutch of the global view that a spatial visual offers. But the fundamental rules of this real estate exchange remain the same. If you fix one slider in place and watch the other 3 trade off, this is basically what it means to take a slice of the 4D sphere to get a small 3D sphere, in much the same way that fixing one of the sliders for the 3-dimensional case gave us a circular slice when the remaining 2 were free to vary. Now, watching these sliders move about and thinking about the real estate exchange is pretty fun, but it runs the risk of being aimless unless we have an actual high-dimensional puzzle to sink our teeth into. So let's set aside the sliders for just a moment and bring in a very classic example of something that seems reasonable and even dull in 2 and 3 dimensions, but which is totally out of whack in higher dimensions. To start, take a 2x2 box centered at the origin. Its corners are on the vertices 1, 1, 1, -1, -1, 1, and -1, -1. Draw 4 circles, each with radius 1, centered at these 4 vertices, so each one is tangent to 2 of its neighbors. Now I want you to think of the circle centered at the origin, which is just large enough to be touching those corner circles, tangent to each one of them. What we want to do for this setup, and for its analogies in higher dimensions, is find the radius of that inner circle. Here in 2 dimensions, we can use the Pythagorean theorem to see that the distance from the origin to the corner of the box is the square root of 2, which is around 1.414. Then you can subtract off this portion here, the radius of the corner circle, which by definition is 1, and that means the radius of the inner circle is square root of 2 minus 1, or about 0.414. No surprises here, that seems pretty reasonable. Now do something analogous in 3 dimensions. Draw a 2x2x2 cube, whose corners have vertices 1, 1, 1, 1, 1, -1, on and on and on. And then we're going to take 8 different spheres, each of which has a radius 1, and center them on these vertices, so that each one is tangent to 3 of its neighbors. Now again, think about the sphere centered at the origin, which is just large enough to be barely touching those 8 corner spheres. As before, we can start by thinking about the distance from the origin to the corner of the box, say the corner at 1, 1, 1. By the way, I guess I still haven't yet explicitly said that the way distances work in higher dimensions is always to add up the squares of the components in each direction and take the square root. If you've never seen why this follows from the Pythagorean theorem just in the two-dimensional case, it's actually a really fun puzzle to think about, and I've left the relevant image up on the screen for any of you who want to pause and ponder on it. Anyway, in our case, the distance between the origin and the corner 1, 1, 1 is the square root of 1 squared plus 1 squared plus 1 squared, or square root of 3, which is about 1.73. So the radius of that inner sphere is going to be this quantity minus the radius of a corner sphere, which by definition is 1. And again, 0.73 seems like a reasonable radius for that inner sphere. But what happens to that inner radius as you increase dimensions? Obviously, the reason I bring this up is that something surprising will happen, and some of you might see where this is going. But I actually don't want it to feel like a surprise. As fun as it is to wow people with counterintuitive facts in math, the goal here is genuine understanding, not shock. For higher dimensions, we'll be using sliders to get a gut feel for what's going on. But since it's kind of a different way of viewing things, it helps to get a running start by looking back at how to analyze the 2- and 3-dimensional cases in the context of sliders. First things first, how do you think about a circle centered at a corner, like 1, -1? Well, previously, for a circle centered at the origin, the amount of real estate belonging to both x and y was dependent on their distance from the number 0. And it's the same basic idea here as you move around the center, it's just that the real estate might be dependent on the distance between each coordinate and some other number. So for this circle, centered at 1, -1, the amount of real estate belonging to x is the square of its distance from 1. Likewise, the real estate belonging to y is the square of its distance from -1. Other than that, the look and feel with this piston dance trade-off is completely the same. For simplicity, we'll only focus on one of these circles, the one centered at 1, 1. Now ask yourself, what does it mean to find a circle centered at the origin large enough to be tangent to this guy when we're thinking just in terms of sliders? Well, notice how this point of tangency happens when the x and y coordinates are both the same. Or phrased differently, at the point of this corner circle, closest to the origin, the real estate is shared evenly between x and y. This will be important for later, so let's really dig in and think about why it's true. Imagine perturbing that point slightly, maybe moving x a little closer to 0, which means y would have to move a little away from 0. The change in x would have to be a little smaller than the change in y, since the real estate it gains by moving farther away from 1 is more expensive than the real estate that y loses by getting closer to 1. But from the perspective of the origin point, 0, 0, that trade-off is reversed. The resulting change to x squared is smaller than the resulting change to y squared, since when real estate is measured with respect to 0, 0, that move of y towards 1 is the more expensive one. What this means is that any slight perturbation away from this point where real estate is shared evenly results in an increasing distance from the origin. The reason we care is that this point is tangent to the inner circle, so we can also think about it as being a point of the inner circle. And this will be very useful for higher dimensions. It gives us a reference point to understanding the radius of that inner circle. Specifically, you can ask how much real estate is shared between x and y at this point when real estate measurements are done with respect to the origin, 0, 0. For example, down here in 2 dimensions, both x and y dip below 0.5 in this configuration. So the total value, x squared plus y squared, is going to be less than 0.5 squared plus 0.5 squared. Comparing to this halfway point is really going to come in handy for wrapping our mind around what happens in higher dimensions. Taking things one step at a time, let's bump it up to 3 dimensions. Consider the corner sphere with radius 1 centered at 1, 1, 1. The point on that sphere that's closest to the origin corresponds to the configuration of sliders where x, y, and z are all reaching down toward 0 and equal to each other. Again, they all have to go a little beyond that halfway point because the position 0.5 only accounts for 0.5 squared, or 0.25 units of real estate. So with all 3 coordinates getting a third of a unit of real estate, they need to be farther out. And again, since this is a point where the corner sphere is tangent to the inner sphere, it's also a point of the inner sphere. So, with reference to the origin, 0, 0, 0, think about the amount of real estate shared between x, y, and z in this position, corresponding to the tangent point. It's definitely less than 0.75, since all 3 of these are smaller than 0.5. So each one has less than 0.25 units of real estate. And again, we sit back and feel comfortable with this result, right? The inner sphere is smaller than the corner spheres. But things get interesting when we move up into 4 dimensions. Our 2 by 2 by 2 by 2 box is going to have 16 vertices at 1, 1, 1, 1, 1, 1, 1, -1, and so on, with all possible binary combinations of 1 and -1.
Okay.
What this means is that there are 16 unit spheres centered at these corners, each one tangent to 4 of its neighbors. As before, we'll just be focusing on one of them, the one centered at 1, 1, 1, 1. The point of the sphere closest to the origin corresponds to the configuration of sliders where all 4 coordinates reach exactly halfway between 1 and 0. And that's because when one of the coordinates is 0.5 units away from 1, it has 0.25 units of real estate with respect to the point 1. We do the same trick as before, thinking of this now as a point of the inner sphere and measuring things with respect to the origin, but you can already see what's cool about 4 dimensions. As you switch to thinking of real estate with respect to 0, 0, 0, 0, it's still the case that each of these 4 coordinates has 0.25 units of real estate, making for a total of 1 shared between the 4 coordinates. In other words, that inner sphere is precisely the same size as the corner spheres. This matches with what you see numerically, by the way, where you can compute the distance between the origin and the corner, 1, 1, 1, 1, is the square root of 4, and then when you subtract off the radius of one of the corner spheres, what you get is 1. But there's something much more satisfying about seeing it, rather than just computing it. In particular, here's a cool aspect of the fact that
I need to stop this. Oh god. So I used to be quite good in math, but these things, damn,
We start with a
it's
point.
somewhat confusing. How to measure the 10th dimension?
Like the point we know from geometry, it has no size, no dimension. It's just an imaginary idea that indicates a position in a system. A second point, then, can be used to indicate a different position. But it, too, is of indeterminate size. To create the first dimension, all we need is a line joining any 2 points.
Is this a 240 video? Yeah, that's amazing.
A first-dimensional object has length only, no width or depth. If we now take our first-dimensional line and draw a second line crossing the first, we've entered the second dimension. The object we're representing now has a length and a width, but no depth. To help us with imagining the higher dimensions, we're going to represent our second-dimensional object as being created using a second line, which branches off from the first. Now let's imagine a race of two-dimensional creatures called flatlanders. What would it be like to be a flatlander living in their two-dimensional world? A two-dimensional creature would have only length and width, as if they were the royalty on an impossibly flat playing card. Picture this. A flatlander couldn't possibly have a digestive tract because the pipe from their mouth to their bottom would divide them into 2 pieces. And a flatlander, trying to view our three-dimensional world, would only be able to perceive shapes in two-dimensional cross-sections. A balloon, for instance, would start as a tiny dot, become a hollow circle which inexplicably grows to a certain size, then shrinks back to a dot before popping out of existence. And we three-dimensional human beings would seem very strange indeed to a flatlander. Imagining the third dimension is the easiest for us, because every moment of our lives, that's what we're in. A three-dimensional object has length, width, and height. But here's another way to describe the third dimension. If we imagine an ant walking across a newspaper which is lying on a table, we can pretend that the ant is a flatlander, walking along on a flat two-dimensional newspaper world. If that paper is now folded in the middle, we create a way for our flatlander ant to magically disappear from one position in his two-dimensional world and be instantly transported to another. We can imagine that we did this by taking a two-dimensional object and folding it through the dimension above, which is our third dimension. Once again, it'll be more convenient for us as we imagine the higher dimensions if we can think of the third dimension in this way. The third dimension is what you fold through to jump from one point to another in the dimension below. The first 3 dimensions can be described with these words: length, width, and depth. What word can we assign to the 4th dimension? One answer would be duration. If we think of ourselves as we were 1 minute ago, and then imagine ourselves as we are at this moment, the line we could draw from the 1 minute ago version to the right now version would be a line in the 4th dimension. If you were to see your body in the 4th dimension, you'd be like a long undulating snake, with your embryonic self at one end and your deceased self at the other. But because we live from moment to moment in the 3rd dimension, we're like our 2nd dimensional flatlanders. Just like that flatlander who can only see 2-dimensional cross-sections of objects from the dimension above, we, as 3-dimensional creatures, can only see 3-dimensional cross-sections of our 4th dimensional self. One of the most intriguing aspects of there being one dimension stacked on another is that down here in the dimensions below, we can be unaware of our motion in the dimensions above. Here's a simple example. If we make a Mobius strip, take a long strip of paper, add one twist to it, and take the ends together, and draw a line down the length of it, our line will eventually be on both sides of the paper before it meets back with itself. It appears, somewhat amazingly, that the strip has only one side, so it must be a representation of a 2-dimensional object. And this means that a 2-dimensional flatlander, traveling down the line we just drew, would end up back where they started without ever feeling like they had left the 2nd dimension. In reality, they would be looping and twisting in the 3rd dimension, even though to them it felt like they were traveling in a straight line. The 4th dimension, time, feels like a straight line to us, moving from the past to the future. But that straight line in the 4th dimension is, like the Mobius strip, actually twisting and turning in the dimension above. So the long undulating snake that is us will feel like it is moving in a straight line in the 4th dimension, but there will actually be, in the 5th dimension, a multitude of paths that we could branch to at any given moment. Those branches will be influenced by our own choice, chance, and the actions of others. Quantum physics tells us that the subatomic particles that make up our world are collapsed from waves of probability simply by the act of observation. In the picture we are drawing for ourselves here, we can now start to see how each of us are collapsing the indeterminate wave of probable futures contained in the 5th dimension into the 4th dimensional line that we are experiencing as time. What if you wanted to go back into your own childhood and visit yourself? We can imagine folding the 4th dimension through the 5th, jumping back through time and space to get there. But what if you wanted to get to the world where, for example, you had created a great invention as a child that by now had made you famous and rich? We can imagine our 4th dimensional selves branching out from our current moment into the 5th dimension. But no matter where you go from here, the great child inventor timeline is not one of the available options in your current version of time. You can't get there from here, no matter how much choice, chance, and the actions of others become involved. There are only 2 ways you could get to that world. One would be to travel back in time, somehow trigger the events that caused you to come up with your invention, then travel forward in the 5th dimension to see one of the possible new worlds that might have resulted. But that would be taking the long way. The shortcut we could take would involve us folding the 5th dimension through the 6th dimension, which allows us to instantly jump from our current position to a different 5th dimensional line. In our description of the 4th dimension, we imagine taking the dimension below and conceiving of it as a single point. The 4th dimension is a line which can join the universe as it was 1 minute ago to the universe as it is right now. Or in the biggest picture possible, we could say that the 4th dimension
Oh my brain is hurting. My brain is hurting.
And 7-dimensional objects. One point has 0 dimensions. Double the points, and you have 1 dimension. Double the points again, and you have 2 dimensions.
Okay, interesting.
Double the points again, and you have 3 dimensions.
Nice. Okay, what now?
Double the points yet again, and you have 4 dimensions.
What's with the music?
Skeptical? You're watching this on a flat 2-dimensional computer monitor. In 2 dimensions, it's not possible to have 3 axes, each of which is 90 degrees to the other 2. Yet we accept this picture as a representation of 3 dimensions displayed on a 2-dimensional monitor. In 3 dimensions, it is not possible to have 4 axes, each of which is 90 degrees to the other 3. Yet as with 3 dimensions on a 2-dimensional monitor, we can accept that this is a representation of 4 dimensions. If you remove any one of the 4 axes, you will go back to 3 axes, each of which is 90 degrees to the other 2. Therefore, each of the 4 axes is 90 degrees to each of the other 3. In the same way, we can add a 5th, 6th, or 7th axis, each of which is 90 degrees to all the axes that came before it. Double the points again. And you have 5 dimensions. By continuing to double the points, you can add as many dimensions as you want. 6 dimensions. 7 dimensions. Therefore, we can draw as many dimensions as we want.
Oh god. Oh god. Ooh, I was doing for 1.5 hours. Thank you for watching. I'll need to stop this now. I probably I probably will come day later and do a CC stream. If I don't come, then I'm gonna turn this 1.5 hour stream into a video. So thank you so much for watching me, and see you in another video. Bye bye.